EX75. Still talk about this base extension and this relation with freeness. First part, let R be domain with its fraction field, okay? For finitely generating R modulo M K tensor R with M it's finite dimensional as K vector space. So we have a finitely generated R modulo M. We're not talking about free. So we take free R modules as a particular example, and then we're talking about the dimension we extend scattered to its fraction field. Okay, and so by the last exercise we know that. So this will be a finite dimension with the same dimension equal to the rank of the free R module, but this is not the free R module. This is finitely generated. Then what can we say? What can we say is that we can reasonably talk about the dimension of this K vector space, but on the other side, we cannot talk about the rank of M. But what we can talk about is generating set. So we claim this dimension is the maximal number of R-linearly independent elements. In M. And is a lower bound. On the size of spanning set for M. In other words, you cannot find spanning set, which means R spanning set of M with less than dimension K elements, and you can find dimension K elements of dimension K number of R linearly independent elements. Right, you can find R linearly independent elements. You can find dimension K k are linearly independent elements. Of course, you can find less than dimension k are linearly independent elements, but when you put less than dimension k, you can never spanning this M R linearly. In particular, the size of each linearly independent subset of M is less or equal than the size of each spanning set of M. Because this spanning set of M is bigger or equal than dimension of K tensor with M, while the size of each linear independent subset is less equal than that. But I think this last statement is very straightforward. A spanning set must consist of a linearly independent, right? I mean, if you have a linear independent set which can span it, you cannot remove it, because if you remove it, then you lose some element. Otherwise, it's not linearly independent. Anyways, this is a more rigorous way to see that. So let's say the proof. Firstly, fxi is, let's write it directly, if x1, x2, xn is a spanning set for M as an R module, then 1 tensor x1, 1 tensor xn span K tensor M over R as a K vector space. This could, at least we can see this from last exercise 74. So the K dimension of this K module is less equal than small n. If now you have R linearly independent elements of M, we claim that one tensor yi is again k linearly independent. I mean, this is not obvious, right? Because when you extend the scalar, you could eliminate some linearly dependence relation. Right? For example, when and I, they are linearly independent over R, but they are linearly dependent over Z. But here the point is that it's not that far. It's just K is Frac R, so you could write any element as denominator in R. So that makes the story not that complicated. So I'm claiming that R linearly independent set is still K linearly independent. This implies that this cardinality of the set D is less equal than the dimension. So in vector space, everything is nice. If you have a linearly independent set, then the cardinality must be less equal than the dimension of the vector space. That's okay. This is saying that any linearly independent set is cardinality is less equal than dimension. That's our first part of the claim, right? This is the maximal number of our linearly independent elements. There is hides two false information. The firstly is any D is less equal than this dimension. Secondly, there should exist some T equal to the maximal number, which means exists a linearly independent set. Yeah, I think that's the nice part of the theorem. It tells you that, okay, how do I compare the dimension after the scalar extension with the previous module? I'm not talking about the rank of the previous module. What I'm talking about is the number of R linearly independent elements. Actually, I'm saying that I could find at most and indeed a set of R linearly independent elements with its numbers the same as the dimension of the vector space after scalar extension. In other words, I'm using this scalar extension to give some information about this finitely generated R module M. I could say something about this finitely generated R module M using after scalar extension, because after scalar extension, things become transparent because it's a vector space. I could use this vector space to tell me some information about finitely generated R module, which is not that obvious. For example, in particular here, says the size of each linear independent subset of M is less equal to the size of each spanning set of M. So this is a phenomenon very obvious in vector space, but when it's come to finitely generated R modules, takes some work, right? Okay, so let's prove this. Suppose summation I from 1 to D so this is linear independence. I mean, when I is linear independence, is R a linear independence, so we want to show that it's K linearly independence. So we want to show that all the CI equals 0, right? What do we do is, because it's in the fraction field, we could find the common denominator for all of those CI. And then we could rewrite this tensor product as just move this AI to the right hand side of the tensor. And on the left hand side is only left with 1 over b, so we can move this outside. This become a elementary tensor. Right, and this falls into where K tensor with R over M, and recall that if you are in case, here you have R, here you have a K vector space, here it's some R module, then we know what is the case this is 0. And what it mean an element being 0, right? So by our assumption this is 0, and so we know for very general case a tensor M is 0 if and only if A equals 0 or M is in M tar. Recall this is look at exercise 66 maybe, I'm not sure. And so this implies that 1 over b equals 0, or this AI, yi summation equals 0 in M. So this is not 0. And so this implies this is the case. But then yi is R linearly independent. And so all the AI are equals to 0. If all the AI is equals to 0, this is telling you that all the CI is equal to 0. So this already proves D is less equal than the dimension. But we want to show that there exists some y1, y2, y T with T equal linearly independent, R linearly independent, is T equal, right? And only so we say that the dimension is the maximal number of linearly independent elements of M over R. So let E1, E2, ED be a linearly independent subset of M. Where small d is maximal. So no matter you use axiom of choice, let me think, I don't think that's necessary. It's basically because D is already proved to have upper bound. Dimension K tensor with M over R. And so maybe you need Zorn's lemma to show the existence of the maximal the existence of the maximum of number of linearly dependent subsets. Yeah. So a better way to write this, let me write this. Where M is the maximal D. So then let's show this D equals, this S equals the dimension for every M in big M, then this must be linearly dependence, R-linearly dependence. So there exists some AI in K, not all zero, such that AN E1 plus AS ES plus AS plus 1 M equals 0. And AS plus 1 is not 0. If not, A1 equals A2 equals AS equals 0, and then this tells you that AS plus 1M is 0, and then what can we say? I mean, wait. M is just a finitely generated R module. R is a domain. Sorry, so stupid. If not, it means that AS plus 1 equals 0. Then this equals 0, then this is saying that all the AI equals 0, contradiction to our assumption that not all 0. Sorry, stupid. Now let's look at in this K vector space. This expression tells us we have this. This is inside this K vector space. And you know that we have proved that if you have R linearly independent set, then one tensor with it is K linearly independent. And so we know that one tensor EI, they form K linearly independent. Right. Anyway, this is just a linear relation, linear dependence relation in K, and this tells you that this could be written as a linear combination of this one tensor EI, and in particular, it's telling you that, so here is AS plus 1. This could be written as a linear combination of those one tensor EI. And then what? Let's think about it. And then this is saying that any one tensor M is in the span, K linear span of one tensor EI, and they are linearly independent. K linearly independent. But how far is this from a general element of this K vector space? It's not too far, it's just up to scalar multiplication. So any element, just of the case K tensor M. And so, or a sum of this. So it's just, and so again it's in the K span of one tensor EI. So this is telling us that this one tensor EI form a basis of this tensor product. And so that S is the dimension of tensor M over R. Remark. Firstly, while M has at most dimension K tensor M over R, linearly independent element, and this upper bound is indeed achieved by what I have just proved. Each spanning set has at least dimension many elements, but this lower bound is not necessarily achieved. examples, which means you might not have a spanning set have exactly the dimension many. Which means this is the difference between a finitely generated module and a free module, right? You could find at most dimension many linearly independent elements, but you cannot guarantee that they just become a generating set. There's something in between. For example, if R is not a field, and M is a torsion, if for example M equals R quotient I for I a non-zero proper ideal, then what do we have? Then this K vector space become 0. This is what we have proved. If this, we replace this with M tar, then this is 0. But the dimension, but the generating or spanning set, the size of spanning set don't have to be 0. Cannot be 0. Let's say bigger than 0. Second remark. It's not true that dimension is finite. It implies M is finitely generated. As our module. For example, Q tensor over Z with Q is isomorphic to Q, but Q is not finitely generated as Z module. This is what we have proved already, exercise before. Third remark. The maximal number of linearly independent elements R module M. Well, R is domain. Is called the rank of M. So usually this is rank is only defined for free module, right? So here we also define it for this finitely generated. Wait, do I need to require this to be finitely generated? I think so. I think I need to restrict to the case to use our result first exercise and then to define the maximum number of linearly independent elements of R module M, we need to require this M to be finitely generated R module. Maybe you could still use our lemma to reasonably define it without requiring it to be a finite generated R module. So this definition, of course, is consistent when this M happens to be a free R module. It's the same rank. Fourth remark. For domain R with fractional ideal K, a finitely generated R module M has rank, just define rank 0 if and only if M is a torsion module, right? Why? So let's see when put this as second part of the exercise proof. We have, actually we know this rank is the same as the dimension of this K vector space, but this is by our proof isomorphic to this. Actually, we don't even know this. This is just one more remark. The proof of this is direct. So that dimension rank 0 should equals to the dimension of this K vector space. Right, and so if this is 0, this implies this is 0, but by our result before we know this is 0 only when K is 0 or M is torsion. So this implies M is torsion. Remark. The remark is this. This is telling that the rank of this is the same as the rank of this. I claim this is K linear. What we know before is R linear. Check, this is also K linear. Okay, when elements of K, you could write it as a fraction, denominator is R, and then what that R linear tells you, check it. So